Hey guys, in this video we will implement the emotion recognition problem. The workflow is as follows. First, we will train the model Vgg16 on FIR 2013 by Pytorch Lightning. FIR 2013 is an emotion recognition dataset. And after that, we will use the train model for inference. We will do inference on image, videos, and live webcam. In inference time, for each inference image, we will extract facial regions using the API face recognition and then class the emotions of the extracted regions. Here are main steps throughout the notebook. First, we will do data processing. The data that we use is FIR 2013, which comes in a CSV format. You can download this data on Cargo, or you can download it in the Google Drive link that I posted in the notebook. After handling the data, we will train it on Vgg16 with Pytorch Lightning. In the second step here, I will also implement Vgg16 from scratch. I recently learned Pytorch Lightning, so please give me any comment if you find details that I should have improved. The last part will be deployment of the model. Now let's start the coding. For this to work, you need to install some dependent Pytorch Lightning and face recognition. And then you will need to import relevant modules like Torch Visions, Torch NN, and so on. Now let's come to data processing. Here is the link to the dataset FIR 2013 that I use. Well, maybe before we do the coding, let me show you how the data look like. This file is big, so perhaps it takes some time to open. So here on this data, we have many rows that correspond to the number of image which we have. On each row, we have the index, which is the emotion. We have the pixels. This is the image, and we have the usage for the image. It can be used for training, or for testing, or for validation. So here we should keep in mind that the first value for each row is the emotion ID, the second value is the pixel values, and the third one is the purpose of the image: training, testing, or validation. Now let's load the data. Here I already put the data file in the folder on the left so that I can load it directly in my notebook. The name of the file is FIR 2013. This is a CSV file. First, I will create a few empty arrays. Chain X, chain Y are the arrays for the data and the label. I have public test X, public test Y as empty arrays for validation set that I would use later. And here I also have private test X, private test Y as data for testing that will be used later. We open the file in reading mode, CSV in. First, let's read the data. Now we will look through the row in data. As we have seen earlier, the last entry of the row will be indicating the purpose of the data, whether it's training. In this case, there are three purpose: training, public test, or private test. Whenever it's training, we are going to put the data into the train set. So I will create temporary array. So for each pixel, the second last row are the pixel value, but they are separated by an empty space. So we need to split them out and join them one by one. So yeah, okay, too fast. So now we have all the pixel value stored in temp. We just append it to the train arrays. Okay, magically here, Collab already do me the favor to do append the label. Chain Y, we need to append the first entries, which is the label of the data. So we will repeat this for 2 more blocks. So when we have public test, we do the same, but now we need to change this to public test. And if we have private test, we will put them in private test arrays. Well, right now we get the arrays of data. We will convert them into NumPy arrays. So convert to NumPy arrays. NPS array chain X, NPS array chain Y, and we will repeat this for the public test set and the private test set. And the same thing for private test set. So now we get our data stored in the NumPy array. Let me resize it, because right now the pixels are all flattened in a row, and here we want them to come in the form of an image of size 48 by 48. So let's reshape the data. Yeah, so we will do so for the same public test and private test. So now let's print out the shape of the data. So we have train data, and okay, you have public test data, we have private test data. Yeah, so let's see how it goes. Well, while it is running, it takes some time to load this file. This file is not a small one. It's about 300 megabyte. while it is running, we will try to plot a few images. So we'll import matplotlib. Okay, so here it is finished. For the train data, we can see that we have 28,000 images. Each has resolution 48 by 48. All these are grayscale image. For public test and private test, each have about 3,000 images. Now let's display a few images. We will display maybe 16 images from the train set. Here I not only want to display the ID of the emotion, I want to display the name of the emotion. Well, I have done this before on Google Colab, so I think that's why they always suggest me the correct thing that I need to write here. But let me go through the emotion to see whether they are really correct. Yeah, looks all good. You will set a figure size. Well, I want to display 16 images in 2 rows. So the size, the images here are quite small, so I think the height 4 will be enough. This will be 2 by 8. Yep. I don't want to show the X and the Y scalings. And here I want to put the label for the image in the x-axis. Emotion. Okay. Let's see. Why I am sure need additional argument. Well, what is happening? Well, I haven't shown anything here yet. Yeah, that's the, because I've been using the auto-filling. Alright, so here you can see roughly how the image look like. They are all face images classified with the emotions. So at this point we have the data put in the arrays that are in correct shape. However, to be able to train the data, we will need to put them in a custom data set. Basically, I will augment the data using touch vision.transforms. So next we will create a custom data set. I need data set. For 2013 data set. We will init it with keyword split that is default to train, transform, and we also want to put all the data on CUDA so we can train them later. Super init. Let's set the attribute first. self.transform, self.split, and device. If split equal to train, we initiate train data to the array that we have created above. If split equal to the keyword that I want will be public. Yeah, no need to put in test. Public test x, public test x, public test y equal public test y. Else if we have private keyword, then we initiate this attribute. Alright, so the main thing here is to get an item from this custom data set. Well, to create a custom data set, basically we need to define the get item method and also the length method. For the get item method, we want to get an item at some certain index. So here in this case we want to return a pair image and label at index idx. If self.split equal to train, our image and label will be taken from train set. If if it is public, it will be taken from the public test set, and I'm not sure if it's a bad habit to make space between if, but I guess I just keep them on continuous slice. Private, they should be taken from private test set. Now, we make an if for elf.transform. If elf.transform is not none, then we want to apply transform on the image. The transforms that we use will be touch vision dot transforms, and it only apply on an image. It doesn't apply on an array. So first I will convert the array to an image. Right now our image here are just array. We need to convert them to image type first. Image from array, image. We also want the data type to be unsigned integer, and then now we can apply transform to the image. We also want to move to the correct device. I want to make the label as tensor as well. I should have set self.device. Should be corrected now. All right. So lastly, we need to define the length method. If it's train, if we have train, then we simply return the length of train y. So if we have public, we'll return the length of public test y, and if we have private, we will return the length of private test y. Alright, so that is the custom data set. Now we are okay. No module touch untills touch utils. Let's see any. Yeah, there should be no problem here. Now we are going to create a data loader from this custom data class. So get data loaders for training. We will import transform. We will import data loader from touchvision.utils. This data loader here. Well, for data augmentation, I will I will transform each of the train image by randomly crop the image into size 44 by 44, randomly horizontal flip the image. So my transform for the train set here will be a composed of not resize, will be composed of random crop on the size 44, followed by a random horizontal flip, and then convert to tensors. So I will do these three as the data augmentation. Well, the trick that I use in this case is for the test image. So for each test image, I will randomly crop into 10 sub-image, and the final prediction for a test image prediction will be equal to the average prediction over these 10 sub-image. I found that this trick actually improved the accuracy of the test set by 1%, 1 or 2%. Of course, here it will. The downside is that it will slow down the inference, because you need to give prediction on 10 sub-image and take the average of them. However, we have higher accuracy. So transform on test and validation set will be a compose of random crops, which is called 10 crop cut size, and transform dot lambda. Well, that is the one. Transform dot lambda, and here yeah, we stack all these. All right, so now we will create the data loader. The batch size that I use is 128. First, let's have the train data. Will be taken from the custom data class for 2013. We set split to train, and we set device to CUDA. Transform equal transform train and device to CUDA. For okay, we also should set up the train loader here. Shuffle equal true. Yeah. Batch size equal batch size, and shuffle choose. Now we will do the same for well, validation data. Validation data will be taken from public test data, and validation loader yeah, so we don't shuffle on validation and test. The last one is test data. Okay, they look good to me. Let's load them first. Pytorch Vision has no attribute random crop, so here should be random crop. No attribute random horizontal flip. All right, maybe before we proceed, we want to check a batch. We check the shape of a batch. Batch label. We will take a batch from the train loader to check the shape. Let's create an F string input train batch. So batch dot shape input train data batch, and we have label input train data. Label here will be label dot shape. And let's print out the device. So here I want to put all the data on CUDA. Alright, so here for each batch, it has shape 128 times 1 by 44 by 44. So we have 128 images, and each has shape 1 by 44 by 44. The device that we have here is CUDA. Yeah, actually I have just implemented the data loader. In the second part here, we are going to train the data on Vgg16 with Pytorch Lightning. So first, we are going to create Vgg16 from scratch. Well, of course, we can always load the pre-trained model and train from the pre-trained model. However, for practice, I want to create it from the scratch. First, you will need to import Pytorch Lightning and a few dependencies from Pytorch Lightning. Here, I will go through the steps that I used to create Vgg16 for this problem. So here, first I want to load the original Vgg16 and then recreate this model. Well, this original model can be loaded from touchvision.models. So here you can see in these models there are 3 blocks. One is feature extractor, and after feature extractor we have an average pooling, and the last one is classifier. In feature extractor here we have sequence of convolutions followed by ReLU, and there are max pool. So here I am going to use this feature extractor to get the with average pooling. The classifier will be a simple nn.linear with output equal to the number of class for my problem. So here I will create this model from the scratch. So the layers here, the output channel of the layers in the feature extractor here are 64, 64. So all these means we have convolution layers, a convolution layer with kernel size 3 by 3, and the padding is always 1. So first we have 2 convolution layer with 64 channels, and after this we have a mux spool layer. After mux spool layer we have 2 convolution layer followed by a mux spool, and a few 3 more convolution layer followed by a mux spool, and so on. So here I will create a list which indicate the layers 64, 64, M, 128, 128, M. Well, I want to be careful here. 256, 256, 256, M, and 512 3 times M, and then 512 3 times M. 256, 256, 256, M, 512, 512, 512 3 times M, and 512, 512 3 times and M. Okay, so this is the list of layers that correspond to the feature extractor. So let's create Vgg16 from this layer. Here I want to subclass the lightning module. Well, for the init method I need in channel. You can set in channel equal to 1 because in this case the model take in the image of the data that has only 1 channel, or maybe I will just put it here and later I will initiate it with 1. The number of classes here will be the number of emotions, that is 7. I will also set dropout to 0.5. Learning rate, the start learning rate will be 0.01. Okay. First, let's just set the attribute here. Num class equal num class self dot learning rate self dot dropout. Well, in fact, for self dot dropout, I want to set a dropout layer and end dot dropout. So now we are going to create Vgg16 backbone or feature extractor. So in this sequence, I will look through this sequence of layers. So whenever we have an M here, that means a mux spool layer. Whenever we have a number here, that means a convolution layer followed by a ReLU. So for layer in layers, if it is M, then well, we should have initiate the backbone with a list. We will just append this mux spool to the backbone. Mux spool kernel size and stride both are equal to 2. It should be backbone. Else, in the case we have a number, we will have a number here, so that is a convolution layer followed by a ReLU. So here and so we want in channel layer kernel size is 3, padding is 1. Right. Well, before using the activations, I would normalize the output first, and then we have nn dot preload. And for the nn dot preload here, we set in place is true. Well, and for the next layer to take on the channels, the correct channel, we need to set in channel equal to the layer. Well, so that is a backbone or the feature extractor. But if you look here, so we have done with the features block. Vgg16 also use an adaptive average pooling. At this point, I want my output to be a single logit, so I would use adaptive pooling of size 1 by 1. Self dot backbone. I will adaptive average pooling shape 1 by 1, just to set the output at this point to be a single number. And now we will create a sequential module for the backbone. Yeah, because we have a list and we can create a sequential module by using the list. So all that left is the classifier. Well, so I simply choose an n dot linear. So note that at this point here, the out channel is 512. So we want to classify into 7 emotions. That is the number of class in our case. So we have nn dot linear 512 to number of classes. Well, in fact, we don't need to choose self dot. We just need number of classes. Okay, we also want accuracy matrix for our model. We would use touch magic dot plus specification dot accuracy. In this case, we have multi-class problem with number of classes equal to number of classes. Next, we will define the forward method. So in our case, we will feed in a batch and the index of the batch. In this forward method, I want to return loss. Well, I was too much attracted by the auto suggestions and forget that I am implementing the lightning module. So in lightning module, I need a change step. I need a change step, which is very similar to the forward in the usual nn dot module. So we want to return the loss. So for the batch here, we want to extract the data and the label of the data. So I will put them as x and y. The predictions can be done by the forward method. The forward method here I will implement later. So note that at this point, prediction logits, because we never apply any activation function on top of the logits. Well, So now we will put in the loss. We will compute the loss using cross entropy between prediction and the label, and we want to log in the loss together with the accuracy. So cell.accuracy, prediction and labels, yeah, and return the loss. Well, and then next we are going to implement the validations step and test step. However, to avoid confusion on the forward method, I will implement these two later, and I will implement the forward method first. So for the forward method here, first we feed the data through the backbone. So note that X is a batch of data, and it has shape 1 to 8 times 1 times 48. Actually, it should be 44, because X here come from, let's say, the train loader, where we already crop the image into size 44 by 44. After we apply the backbone, the output channel is 512. So the shape at this point will be 500. Output channel will be 512 times 1 times 1. Note that we apply the adaptive pooling of size 1 by 1. Right? So here we have the last two dimension equal to 1 by 1. Next, we are going to apply dropout and classifier, but I want to get rid of these last two dimensions, so I will squeeze X on the last two dimension. And drop out and classifier. Yeah, self-classifier X, and then return. Well, to make it clear, here the dimension is 128, 512, 128, 512, and the last one give us dimension 128 times 7, because there are 7 classes in our data set. All right, that's the forward method. Next, we will get the validation step. This one is a little tricky because our input, let's extract X and Y from the batch. So X here has shape 1 to 8 times 10 times 1, 44, 44. Well, remember that we for validation and test set, we randomly crop an image into 10 sub-image and give 10 prediction for each of these sub-image. The final prediction is the average of these 10 predictions. So each image will be cropped into 10 sub-image. The original image has shape 1 by 48 by 48. After doing the transform, we have shape 10 times 1 times 44 times 44, and 1 to 8 here is the batch size. So here X equal to this, and we take average prediction over 10 sub image for the final predictions. So here I'm going to run through all the 10 sub-image and then take the average. So first I will transpose x between the first two coordinates. So the x transpose in this case we have shape 10, 1, 2, 8, 1, 44, 44. And I will proceed the sub-image here by batch. Well, let's set the loss and the predictions. So first let's set them to zeros. Self.num classes device equal to device. Well, I should have set device in front also. In this case, note that I want to give the final prediction as in the shape 128 by 7 because we have 128 images in the batch and we have 7 classes. So here let me set device. Now we go loop for I in range x dot size 0. We will forward xi, right, and then add it to the predictions. The loss in this case is the cross entropy between prediction and y. So what we do here is prediction and loss for sub-image I. So after this, we need to divide by, we need to take the average. So we divide by 10. This is 10. And we will log in the validation loss with the validation accuracy. For validation step and test step, we don't need to return. So yeah, that's it for validation step. The test step is almost identical. So here we just change the name and the rest is identical because we also use the same trick. We have 10 sub-image and we need to take predictions over these 10 sub-image. The last one that I want to implement is to configure the optimizers. Well, the optimizer that I use is SGD. With momentum. I set momentum 0.9 and weight decay. Well, basically weight decay add a norm into the loss so that it can control the parameter not to be too large. I also have a scheduler. I will use the reduce learning rate on plateau. Plateaued. well, let's set the patient to 5. Yeah. Factor. So here I want to monitor the chain loss. So if the chain loss is not improved by 5 epochs, then we will reduce the learning rate to the factor 0.1. So because I want to monitor the chaining loss, so I set the mod to min here. If you want to monitor other metric like accuracy, so maybe you want the mod to be max. Here I will return a dictionary optimizer and learning rate scheduler. This is another dictionary here. Monitor here will be chain loss and interval, is epoch. So we want to monitor our learning rate every epoch. Note that this is the default choice. Frequency is 1, so this is also default. Now we are going to initiate the model, initiate a trainer and train the model. Initiate the model first. Model is Vgg16 with 1 channel from trainer, which you Pytorch Lightning trainer. We set accelerator to CUDA device 1. We will train for 150 epochs. We also want to set callbacks. So here I already use a model checkpoint as callback, in which I will save the top performing model, and here the mod is max because I want to monitor the validation accuracy. I also want to save the last model. So that's the trainer. Let's load it and see if there's any problem. So it looks good. So here we have GPU and we are going to use it. To train this, we simply call trainer.fit model on train loader, validation loader, and we also want to put in callbacks. All right. Well, the trainer already have callbacks, so there's no need to put in here anymore. You can see now it is training. I trained this before, and for 150 epochs it will take probably over 1 hour to finish the training. To avoid my video getting for too long, so I have trained the model in the back, and here I train it for about 150 epochs. Then the best result come in the epoch 135. Here we can load the model again. If you want to get the path for the best model, you can use trainer.checkpoint callback best model path, and here I simply load this model into the folder here, so I can work on it directly in Google Colab. To load the model, you will call load from checkpoint with the path, and here do not forget to pass in the keyword in channel. I want to evaluate the model on the test set, so I call trainer.test model on the test loader. The accuracy that it achieved on the test loader in this case is about 71%. Well, in the next video, I will talk about how to use the model to do emotion recognition on image, video, and live camera. So here is just how it does on image. I will show you an image. So in this image, there are a lot of people with varying emotions. So you can see the model discover different emotion in the image. There are a few cases that the model failed to detect even the face. For example, this case for this lady here, I guess the reason is from the API face recognition, because the face is not completely shown, so it doesn't detect the face. In this case, the face is occluded by the hand, or in this case, the face is not shown because of the mask. So basically, it works fine for all the normal situations.